All right, good morning, afternoon, good evening, wherever in the world you are. Show me your beautiful faces so that I don't feel so lonely here. There we go. Hey, how's it going, Artemio? Doing good? Alex from Brazil, Alejandro from Argentina.
All right.
Then we got people all over the place. See, Mark, we're not waking up too early today. I was just tired. I was going to do my 5 in the morning stuff, and we start because my son graduated, and then we stay up late just talking and doing stuff. So all right. Hey Ethan, how's it going?
Good. How about you, Wealthy?
Doing good, going good. All right, this is the beginning of session 345 of Tesos and Wi-Fi. This class is part of the Wireless LAN Professionals Wi-Fi design class that we are bringing to the community that speaks English for free, 100% free, and like 98% in English. You know, we still put a few words here in there in Espanol. But today we're going to be talking a different language. Today we're going to be talking about DB math and what's the deal with that. In Wi-Fi, we hear terms all the time that have DBs in them. dBIs, when we talk about antennas, we talk about the gain of antennas using dBIs, like relative to an isotropic radiator or compared to an isotropic radiator. We receive documents all the time about power requirements, like, oh, we recommend that our access points are configured at 14 dBms or 17 dBms, and we're talking dBms, not with an I, with an M, and that's relative to a milliwatt. Also, this is not just in Wi-Fi. We use this in power. We use this for sound. Like I bought a dishwasher last week, and it had a unit of dBA, like compared to absolute silence, how loud is this machine? How much noise does this device generate? DBs, this DB stuff actually, and when we talk about SNR, we talk about that in the last couple of sessions. We talk about 25 dB SNR and higher being really good, but 15 dB SNR not very good. So what is this DB stuff, and why do we use it? Well, it happens that that was last century. The Bell Laboratories, this company that dealt with phones and doing, not just phones, but a lot of stuff, they needed a unit to basically create a unit that measured the loss of power over a wire. Basically, you are installing telephones and you're running wires for these telephones to talk to each other. You inject power, you put power on one end, and then they would have to measure, let's say, a mile down the road on that cable and see how much power was lost to figure out how much more power they had to give this to make it long distances, because, these electrons traveling through this cable attenuate, they get weaker. And so for voice quality and the quality of the signal, they had to know that. So they had a unit called the mile of standard cable, MSC. And that's what they went by. But we're talking big numbers or small numbers. And what they ended up doing was creating a unit that was a tenfold of change in power. So 10 to the 1, raised to the 1 power. And they divided that by 10 and called that unit a Bell in honor of Alexander Graham Bell, a guy that invented that was part of the founder of the company and had a lot to do with telephony. So this unit, the 1 Bell, is what they use as a reference. And then as things start getting gaining traction on, basically other industries adopted that unit. And what exactly is this? Well, since we are talking, like for sound, we are talking exponential numbers. It's a logarithmic function. And logarithms, we're dealing with really big numbers or really small numbers. So we use dBs to simplify this. And again, this is used as a reference. So let's, in many books in Wi-Fi, you will learn about the tens and threes rules. We'll just go through this exercise and basically get familiar with how is it that we convert from dBs to normal numbers, linear numbers, numbers that we can relate and do math with easily. When we talk about these logarithmic functions, it starts getting complicated and numbers start getting really big or numbers are getting really, 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 really small. So we use dBs to simplify. We hear all the time, oh yeah, we design our Wi-Fi to, be next 65 dBm. Actually, before we used to design for next 72 dBm. What does that mean? And why is next 67 better? But then others say, oh no, next 65 is too. And then I had a place, a hotel chain where they say, we need to design our Wi-Fi to be neg 60 everywhere. Like next 60, that's really, really strong. And then other companies, they will use milliwatts. Oh, no. We recommend that our APs are configured at 100 milliwatts. Okay. And then, like, I was at this place not too long ago that I did a survey and the signals were really weak everywhere. It was quiet. And then came to realize all the access points were set to 2 dBms. Okay. So now let's see how we can then figure out these numbers. So Dan, I'm going to teach you how to convert from normal numbers to dBs and from dBs to normal linear numbers that we can relate to. So go ahead and unmute. Can you talk now? Dan Osborne. Let me see where my pen is. I can, there we go. All right. So let me teach you a trick. A good morning for a trick. It's Friday. How's the future going, Dan?
It's pretty warm over here. We're looking at 25. It's about probably 25 degrees Celsius. I'm not sure what that is in Fahrenheit for you guys, but
and raining.
No, it's beautiful.
Oh, lovely. Really?
Yeah.
Okay, so here's the trick I'm going to teach you, Dan. We're going to learn how to convert from dBs, decibels, to normal. Okay. So here's how it goes. On the dB side, I'm going to give you 4 items, 4 elements. I'm going to give you the plus sign, the minus sign, the number 10, and the number 3. With any combination of those 4 items, plus, minus, 10, or 3. That's why they call it the tens and threes rules. We will get to any number in dBs. Okay? So how would you get to 13 dBs if all you have is plus, minus, tens, and threes?
10 and 3 dB.
What was that?
110 plus 13 dB.
So 10 plus 3. 10 plus 3, 13. Do we agree? I mean, it's pretty straightforward. Any elementary school kid can do math and just giving them those 4 items, you'll get to any number. So how do you get to 13 dB? 10 plus 3. That's it. Okay. Then here's the trick. To convert this dB to normal numbers, here's what we're going to do. If on the dB side you have a plus sign and you tilt it, on the other side, it becomes a times. If on the dB side you have a minus sign and you tilt it, you end up with a division sign. This one's pretty straightforward. If on the dB side you have a 10, on the other side you have a 10. A 10 is a 10 on either side, on the dB side or the normal side. And this is the only one that, I don't know, it just becomes a 2. There's no way to tilt the 3 or anything. It's just a 3 is a 2. Okay? So now, it's just a trick. Okay? Then, without doing any math, without thinking, just substituting each one of these units, what does 10 plus 3 become on the other side?
12.
12!
30, right?
See what's the problem, Dan? And the other person said 30.
Yeah,
You should be
kept
doing
kept the ad.
The problem is you started thinking and trying to do math. Don't do math, don't think. Simply substitute each unit as I just showed you. So you gotta go despacito, suave, suavecito. Have you heard that song? You know what despacito means? You gotta go slow. Okay?
20.
So 20. So let's just do it just one at a time. So the 10 becomes
10.
10. Okay. The plus becomes
A times.
a times. And the 3 becomes
A 2.
a
Yeah.
2. So now
I missed the middle. I missed the middle step.
so go ahead and use your calculator. What's 10 times 2? Now we do math.
20.
You did it with a calculator? Man, hey, you're good. Okay. 10 times 2 equals 20. 30 dB is equals to 20. To 20 what?
Milliwatts.
I haven't told you. I haven't put a
Yes.
unit on the dB. See, remember we use dBi, dBm, dBd.
Mm.
As a matter of fact, the antennas, since we talked antennas not too long ago, antennas, there is another unit, dBd, like relative to a dipole antenna, how much gain did this antenna have? And that was like 2.14 or 3.1. I don't remember what the number was. That was like the reference number. So if we say 13 dBms, we put a unit to it now. So 13 dBms, since we talk about this in Wi-Fi for power, energy, these waves, 13 dBm, now that is 20 milliwatts. Okay? Okay. Here's another one. Alejandro, you want to help me with this one? The next one?
Yeah.
Using this trick, and if I give you plus minus tens and threes, how do you get to 27 dBm? Any combination of plus minus tens and threes, how do you get to 27 dBm?
I think that is 10.
10.
Plus
Hang
10
on.
plus
Hang
3.
on, we'll go one. Okay, 10.
Okay. 10 plus 10 plus.
Plus,
7.
hang on. I gotta go slow, man. 10 plus 10, that's 20. Okay.
Plus 7.
Plus what?
7.
Plus, there's no 7. Plus, minus, 10, or 3.
10 plus
Oh,
10 plus 10 minus 3
Yeah.
Okay,
Yeah,
so 10 plus 10 plus 10, then that's 30 minus.
minus
Oh, hang
3.
on. I just put a 10 plus 10, 20 plus 10, 30 minus 3. That's 27. Do we all agree? Okay. Now, what does that then, Alejandro, what does that become on the other side? Because we want to know how many milliwatts is 27 dBm. Now, don't do math, just substitute each unit at a time. Don't think. See, the problem is we start thinking. And once you start thinking, then you're lost. Don't think. Just substitute them. Go ahead.
Okay, 10 times 10 times 10 divided by 3.
Divided by?
By 2, so sorry.
Uh-huh.
2.
Okay. So, 10 times 10? 10 por 10?
100.
100. 100 times 10?
1,000.
1,000. 1,000 divided by 2?
500.
500. 500 what? Since we're using dBMs, that's 500 milliwatts. Okay. How about one more? Okay, who wants to jump into this one? Mark, you want to help me with the next one?
Sure.
Okay, so how do you get to 15 dBMs? All you have is plus, minus, tens, and threes.
Trick question. 3 plus 3 plus 3 plus 3 5 times.
3 plus 3, 6 plus 3, 9 plus 3, 12 plus 3, 15. See, it's really basic math. Okay, what does this then become on the other side?
2 raised to 5.
2 times 2 times 2
times 2 times 2 times 2
times 2. Okay, so 2 times 2?
32. Oh, yeah. Sorry. 4.
2 times 2 is not 32. You got to go one step at a time. 2 times 2?
4.
Times 2?
8.
Times 2?
16.
Times 2?
32.
32. 32 milliwatts. This is pretty easy. Okay, let's do one more, and then we'll see how they actually in the CWNA exam, they will give you some exercises that you're going to have to do DB math, but you don't get a calculator, you don't get to go online, you don't get a table or anything, so you have to know how to do this with just, your fingers, basically. So let's do one more here. Let me just add another page. Okay. Who wants to take on this one? How do you get to, very easy, 14 dBm?
-20 minus 3 minus 3.
20. How do I get to 20? I don't have 20s. I only have plus, minus, tens, and threes.
10 plus 10.
You're going too
10
fast. So 10 plus 10,
10.
that's 20. Then minus 3, 17, minus 3, 14. What does that become on the other side?
10 into 10.
Oh, my pen just died. Hang on. This thing working? Hang on. What is happening today? Holy smokes. First my microphone, then my screen sharing, now my pen. Okay. So 10. Go ahead. Keep going.
Times 10.
Times 10. That's okay. And then?
Divide by 2.
Okay.
And since division is there, so 2 times 2.
Times
The
2. What do I...
division, the division sign is there, right? So, or you can just take it as times 2, right? Because
No.
minus 3 to n.
No, because you're thinking, you're making it very complicated. Just substitute each unit. So it's good so
Just
far.
divide by
Yeah.
2.
Then divide it by 2 again. See, that's it. Okay, what does this then become? So 10 times 10?
20 divided by 4.
That's not 10 times 10 is not 20.
I mean
10 times
100,
10.
sorry.
So 10 times 10, 100 divided by 2.
50,
And 50 divided by 2.
25.
So 14 dBms is equals to 25 milliwatts. That's it. Just a trick. See, the problem is when you start thinking, trying to do math, like you get lost. You end up with wrong numbers. Just plus minus tens and threes, learn the trick. The plus on the dB side becomes a times on the other side. The minus becomes division. 10 is 10, 3 becomes 2. Now, how about we go the other direction? Dan.
Yeah.
If we have 100 milliwatts, how do you get to 100 if all you have is, here, let's just use a different color for this. How's that? How do you get to 100 if all you have is times, division, tens, and twos? How do you get to 100?
10 times 10.
10 times 10. 10 times 10 gives you 100. Now, going the other direction, how many dBms is 100 milliwatts if you have 10 times 10 here? What does that become on the other side?
10 plus 10.
10 plus 10. Why? Because now we're going that direction. A 10 is a 10. A 2 becomes a 3. The division becomes minus, and the times becomes plus. So since we have 10 times 10, that becomes 10 plus 10. So 10 plus 10 equals
20.
20. And since we're talking milliwatts, then the unit is going to be here, dBms. Okay. How about 250 milliwatts? How do we get to 250 if all you have is times, division, tens, and twos? This is getting complicated, huh?
Mm.
Now we have to do more math. Well,
So it's time 10 times 10 times
okay, hang on.
10.
Hang on. 10 times 10, that's 100. Okay.
100 times 10 is 1,000
1,000
divided by 2 and divided by 2.
divided by 2, that's 500, and divided by 2,
By 2. Yeah.
that's 250. Do we agree? Now,
Pretty simple.
what does that become on the other side then? Don't do math. Substitute each unit.
10 plus 10
10 plus 10
plus 10 plus 10
plus 10
minus 3,
Minus 3.
minus 3 minus 3.
another minus 3.
Okay. 10 plus 10, 20, plus 10, 30, minus 3, 27, minus 3,
24.
24 dBm. Does that make sense?
Mm.
It's just a trick. Okay. Now, let me go back over here. This is the table we see in documents. This is a table we see in study guides. You don't have to memorize the table, see? Because now we can just get to any number on one side or the other. Watch this. For instance, let's do 19 dBms. How do you get to 19 dBms if all you have is plus, minus, tens, and threes? Anybody? How do you get to 19? Go ahead, Dan.
10 plus 3 plus 3 plus 3.
16, 19. Okay. Now, what does that then become on the other side?
10 times 2 times 2 times 2.
Times 2. Okay. 10 times 2?
20.
20 times 2?
40.
And 40 times 2?
80.
80 milliwatts. See, it's right there. Just pick a number, any number, and then how do you get to it? Using the plus, minus, tens, and threes rules, and then just convert. Okay. So far, so good. Now, why do we even talk about this stuff? This is a Wi-Fi class, man. Well, it happens that there is something called the inverse square law. This is not unique to Wi-Fi. This is just physics. It was Isaac Newton that in his studies discovered that when you have a source of energy or light or radioactivity, if you double the distance from that source, you're going to have 1/4 of that power left. And then if you double the distance, you end up with 1/4 of the power. So this is just physics. This applies to light, applies to sound, applies to heat. If you're near a fire and it's too hot, what do? Well, you move away a little bit, and then it's not so hot, right? It's just physics. Well, if you have an access point sending energy, sending these waves, as these waves leave the source, they start getting weaker. They start attenuating as they travel through free space. This inverse square law is what software like Ekahau, CDOS, Hamina, Wavelify, IB Wave, all of those are doing. They're just doing math. You have an access point with this radiation pattern at this height, and you put, let's say, 30 dBms of power. Then that power goes through a cable. Those electrons get to the antenna. The antenna, let's say, has a 13 dBi gain. Then what comes out of the antenna is what's called EIRP, effective isotropically radiated power. We'll do a graph and kind of play with this in a little bit. Then that energy leaves the antenna. Those waves start going through, and every time you double the distance, those waves start attenuating at that rate. You double the distance, you end up with 1/4 of the power. Double the distance, you end up with 1/4 of the power. So let's say you have a balloon and you inflate it, okay? And let's say we cover it in guacamole, all right? With guacamole everywhere. And without adding guacamole, you keep inflating that balloon to the size of this room. Now you touch the balloon, it's like, man, I can barely taste the guacamole. Is there less guacamole in the balloon? No, it's the same amount of guacamole. It's just spread in a bigger area. So the particles of guacamole are spread out more because it's the same principle. Without adding energy to the system, as the balloon expands, the particles of guacamole would be separated. And as we keep inflating that balloon to the size of this building, the particles of guacamole are going to be so spread apart that you can barely taste. And is there less guacamole in the balloon? No, it's the same amount. It's spread in such a big area that you can barely taste it. Same thing happens with energy. If you have an access point, omnidirectional antennas, and you send all power really strong, as those waves propagate and dissipate in all directions, when you measure right here, you're going to have just a small, tiny amount of power. Why? Because the energy is spread all over the place where the antenna is designed to send waves. When we talk about antennas, we talk about high gain antennas. Remember the light, flashlight? Once we did the high gain antenna, we were just doing a high gain by focusing the light all in one place. Not by having the light go everywhere, we were just focusing the light on a specific place. And then that circle was really, really strong, really bright. How do we make it brighter? By adding batteries to a system? No. By adding light? No, it was the same light. We were just putting all that light in one single place. The opposite is when you start sending this energy out in multiple places. Every time you double the distance, you end up with 1/4 of the power. As waves, as energy leave an access point, see, those start getting weaker. Now, it says right here, watch. If you start at 0 meters, let's say you have, I don't know, whatever energy you have, but let's say at 1 meter, it says right here that you have 40 dB less than what you had when you started. Whatever number you had at the beginning, at 1 meter is roughly 40. Let's just say that this is, let's say that at 1 meter, we have minus 40 dBms. Okay. Minus 40 dBms. Double the distance from 1 meter to 2 meters. It says here that we lose 6 dBs. Double the distance, 1/4 of the power. So how come 1/4 of the power is minus 6 dBs? Not minus 6 dBms or minus 6 dBis. No, just you lose 6 dBs, 6 decibels. And it said that at 2 meters, the energy, doing this formula, double the distance, quarter the power. It says that at 2 meters, I should have minus 46 dBms. You lose 6 dB. Double the distance, quarter the power, you lose 6 dBs every time you double the distance. How is this possible? Well, let's explain it in more simple terms. Yesterday, I had a piece of cake, carrot cake. You like carrot cake, Dan? It's my favorite. I love carrot cake.
Yep, it's great.
So Dan, let's say we have a carrot cake right here. We need to get 1/4 of this cake. How do we divide this cake in 4 pieces if all we have is times, division, tens, and twos? How can you divide that in 4 pieces?
Divide by 2.
Hang on, hang on. Okay, so you divide by 2, right? Divide by 2.
Yeah.
And then
divide by 2 again.
Divide by 2 again. That's how we end up with 1/4 of that cake. Does it make sense? Pretty straightforward, just math. What does this become then on the dB side? What's divided by 2 on dB?
Minus 3.
Minus 3. And this?
Minus 3.
minus 3 again. Minus 3 is equals to?
Minus 6.
Minus 6. So this minus 6 over here is this minus 6 over here. In Wi-Fi, when you double the distance, you lose 6 dBs. This is just going back to a trick we just learned. Again, if I double the distance from 2 meters to 4 meters, double the distance, 1/4 of the power, you lose 6 dB. This is just physics, okay? We've done this test in class. I used to just get an access point, measure, and then went to 50 centimeters and measure, and then went to 1 meter, and then went to 2 meters, and then went to 4 meters, and then 8 meters, and then I was 16 meters all the way out there. And we were measuring, and it was like almost to the number. Of course, dBs are changing all the time when you're measuring a signal, but it was like spot on. So double the distance from 4 meters to 8 meters. Double the distance, 1/4 of the power in normal. And we said that 1/4 is minus 6 dB. You lose 6 dB again. It's just physics, guys. This is not unique to Wi-Fi. Happens to heat, happens to sound. You notice that in the stereo, some stereos, when you move the volume up or down, it also changes dBs, plus 3 dBs, plus 6 dBs, minus dBs, and it just goes up and down in dBs. That's what it's doing. Okay. Double the distance from 8 to 16, you lose 6 dB. So in here, at 4 meters, we went 6 dB down, so we had minus 46. And if you go 6 dB down, then you end up with minus 52 dBms. Of course, we're just adding the unit right there. Minus 52 dBm. If you measure at 8 meters, you lose 6 dB, minus 52, minus 6, you're going down to minus 58. This is over free space with no obstacles, no obstructions, no attenuation objects. Since this is a Wi-Fi class and we're learning this stuff so we can better design Wi-Fi, and we can better understand how Wi-Fi behaves in space and in an office and in a warehouse and in wherever you're designing Wi-Fi, then this is why we use this. The good thing is all of these programs out there, Ekahau, Ceros, Hamina Wireless, Wavely 5, IB Wave, Tamograph, Tamosoft, all these guys, they do this math for you, Dan. Isn't that good? You don't have to imagine you doing this all the time, just doing math and doing the trick. They will do it for you. So if, let's say, right here in between 4 meters and 8 meters, I add a wall. Okay, we add a wall right there. And let's say then, over here, you come and measure on this side of the wall. Well, let's just forget about that side of the wall. We'll get to it in a second. Let me go back. How do I delete this thing? Okay. So let's say you come and measure again here at 4 meters, okay? And you measure neg 52. So far, so good?
Mm-hmm.
Now you come over to 8 meters. And measure, but you measure neg 65 dBm. If there was no wall over free space, you should have neg 58, right? But now, with that door or wall or window or rack or whatever it is, I mean, I'm just drawing a wall as an example, but whatever obstacle that is, at 8 meters now you measure neg 65. You should have neg 58. So what is the attenuation index, roughly, give or take, of that obstacle that is now in between? Well,
7 dB.
That's going to be roughly 7 dB. See, like when you go to Ekahau that it says, oh, this is a 3 dB drywall, or this is a 10 dB brick. That's what they're saying. A signal through this obstacle loses 10 dB, or loses 3 dB, or loses whatever number it is. Same in Hamina. In Hamina, you can go in and create things, and then it says, this wall loses 2 dB, or it's a really thin pane of glass, it loses 1 dB. Okay, that's how much energy is lost across those guys. So the software
can I ask you one question?
You just did. Thank you very much. Anybody else?
Okay. Well, thank you. So you draw a wall, right? So even with Ekahu or Sidos, when you do measurings, what's the distance that we should be in a position to measure this kind of attenuation?
Excellent question. I may have a piece of pineapple because I need inspiration to answer that question. I like pineapple, man. I grew up selling pineapples in Colombia. All right. At the beginning of this energy here, notice that in that first meter, we lose about 40 dBs. Why? Because from the source, you have this really strong energy. And as this energy leaves the source, it starts dissipating, propagating in all directions. And in a short distance, you lose a lot of energy. Double the distance. Then as you go further, it starts attenuating. Look at this. This curve is kind of like how it goes. And then it settles. You just go back here. What color am I going to use now? Holy smokes, Dan, we're like out of colors here, so it makes sense. Here, let's use black. See, this curve kind of like settles around here. See, it's not too steep when you're looking in this area, like past here. You don't want to be within the first 5 meters from that source, because that's when that energy loses a lot more and the curve is steeper, and that's very, very unstable. I've done, oh, actually, you know what? I did a presentation. Let me see if I have it around here. It was, here, let me see if I have, oh man, that's not it. Because with this, I know it was, oh, here we go, WLPC Berlin. It's a presentation I did. Hang on one second. Let's see if it's coming up. Okay. I'll share this with you in the chat, but let's just do it real quick. Back in the day, I used, an air check, and I had a Ruckus AP, a switch, and I was generating waves, and I started measuring. Watch this. My screen on your screen, okay? Make this bigger. So I placed the access point and then started measuring at different distances, and then happened that every time I moved, like when I was measuring, it changed. And I said, like, there is something wrong with this measuring device, because it was like neck 55, neck 53, neck 58, neck 55, and it was like changing all the time. So I got me another measuring device. And that device was also changing, neck 48, neck 51, neck 52, neck 40, and it was like changing all the time. I said, there's something wrong with this stuff. I talked to Mr. Parsons, and he said, like, that's expected. Because These devices are sending these beacons, these waves, that's what you receive, and they send 10 beacons per second. So you get a whole bunch of beacons, and then it gets the average of that energy, and then it's changing all the time. So I had to leave it in a table so that I didn't move, because every time I move an inch, every time I was breathing and I just moved a little bit, it changed. If I tilted a little bit, it changed. If I switch hands, it changed. So how can I make these things stay and measure? Because I needed to measure distances, to measure attenuation. And then I set them at the same height. Because if you measure here, and then now you go on the other side and measure with another hand, a different height. So I just wanted to be as consistent as possible. So I measure right there. So basically, if you want to play with this stuff, you can do it. Look, you can do it right now with a phone and an access point, your modem in your house. You can just get one of those applications. If you have an Android, get a Wi-Fi analyzer and lock on your AP and measure, and then start walking away at 1 meter, at 2 meters, at 4 meters, and see what the signals they are. So you need something to generate RF. You need something to measure that energy, okay? And then something to measure distances. And then I started plotting those values. Here, the problem is that I had like at 20 centimeters, at 40, at 60, at 8, just like every 20 centimeters, I took a measurement, and then every meter, and then it's like, oh, this is not right because all the steps are different. So I made it all the same, 1 meter increments, 0 meters, 1 meter, and then start measuring in 2.4, and then measuring in 5 gig. Just make this a little bit bigger for you guys. And then notice the graph. And then I said, okay, let's just look at the very first meter. Notice the drastic changes in signal loss. The energy that is lost in that first meter. I lost 13 dBs in here, went from minus 10 to minus 23. That's 13. Well, 10 plus 3, 13, that's 20. So I lost 20 times the energy in here. On this one, it was worse. See, because I went from 0 dBms to minus 19 dBms on the first meter of free space with nothing in between. So this is why you don't want to measure anything within the first 5 meters. Look at this. The amount of energy and the instability that you get in those first 5 meters is pretty remarkable and very easy to spot. Notice that the signals kind of like settle, that curve settles after the 4 or 5 meter mark. Does this answer your question? I know this is kind of a long answer, but you have to understand this well so we can better move forward.
So what you're saying is whenever we measure signal attenuation, we should be away from these objects at least 5 meters away.
With the source, yes, away from the source. Right.
With the
yes.
source. Okay.
So if I have, let's say, an access point generating energy, I don't want to come and put it like right. If this is the wall, you don't want to put the source right here and then measure over here like less than 1 meter and then measure on the other side of the wall. No, you want to have this AP like at least, as you can see, 5 meters away, and then you can come measure in this wall and then measure on the other side. One tool I use these days a lot is the Tesos wave. Let me just stop sharing here for a second. Because this guy, I can just lock. There is an AP tracker. There's a micro app. You get this micro app. Let's wait for this to load. Come on, micro app. While this loads, this guy, hang on, let's see if it's, oh, is that in focus now? You see SSIDs over there? So let me pick one. Let me get this. Let's look for the Home 5. Here we go. There's a Home 5 SSID in channel 52. Oh man, that's backwards for me. Can you read it there? Or is that too small? channel 52, and it's like neg 33, neg 34.
Yeah,
So-
between 30 to 35. Yeah.
Okay, so as I move away, and notice that it's just like it even gives me a decimal. It changes really fast. It's locked into that access point, and I can track it because the closer I get to the AP, see now I'm at neg 29, neg 25, neg 27, neg 21, neg 18, neg 17, neg 14, neg 17. Here we go. That's that access point right there. So you can lock it. And so I use this, go and measure on one side of a wall and measure on the other side of a wall. And then I'll get a difference. Like if on this side I measure neg 45, and then I go to the other side of the wall and then I measure, let's say, neg 48, then I'm going to say, oh, this is more or less a 3 dB loss wall or door or window or rack, whatever it is. So you can use a device like that and then measure on both sides. But you don't want to, again, you don't want to measure within these 5 meters, 4 or 5 meters.
So you
because
just
of the
lean
proximity.
so you just lean the siders onto the wall, right? And
On one side, yeah, measure on one side, yes.
Yeah. Okay, great. Thank you, Fanny. Thank you so much.
All right.
Really helpful.
Yeah. And yeah, you don't have a Cetus, then use a phone or use your computer. See, because I can measure like the signals that I'm getting. Like if I come over here and click on my Wi-Fi sign, then the signal I'm getting now is neg 43. If I move away from that source, then and you have to wait because these devices are just scanning through the channels and doing other stuff and then getting measurements, then this doesn't change as fast as the Cetus because the Cetus is constantly listening, dedicated. This guy is not. I'm right now connected and we're doing stuff and then it's scanning other channels and doing other things and then it gets beacons and then it reports and it changes not as fast. So you have to stay there for a longer period of time. Here's the other thing. Keep in mind that the environment is what you're measuring. So what else is around you? What structure do you have? Do you have metal? You have metal walls, metal doors, metal ceilings, metal surroundings, because then you might have a lot of reflections and then you're going to get multiple readings. You have to measure multiple times, not just once. Oh, 3 dB. Like, no, go measure again. Because when we are talking about attenuation of these waves through free space is one thing. But as I showed you in one of the first sessions, where on a football field, open field, I was getting like strong signal, weaker signal, really weak, and then really strong again. Then, like, why? That defies the laws of physics. Physics says that as you go away, these waves, this energy becomes weaker. And then it was getting stronger because we had reflections of the bleachers in that stadium. So we were just getting bounces of waves. And that happens a lot when you're doing a survey, let's say at a warehouse, that you see an access point and then you don't see it anymore. And then further away, you see it again. How are those waves getting to where you are? So in this case, the free space path loss, that's mathematical calculations that software, Ekahau, Cetus, Hamina, Waveley, 5IB Wave, Tomograph will do for you. But this is just what's being done. If you come then, and again, this is an example they use, if you measure at 50, neg 52 dBm, and then go at 8 meters and measure neg 61, then what's the difference? Well, you should have 6 dB less when you double the distance here. And now it, instead of being neg 58, is neg 61. That's where the minus 3 dB comes from. And those are the units that you see in Ekahau. Oh, this is a 3 dB wall. This is a 10 dB rack, or this is whatever value it is. And I get that question asked all the time. Like, do you have a list of like attenuation objects, like a list that tells me, you know, what a brick wall attenuates? Like a brick wall, we're talking bricks made where? In Norway? Or bricks made down in South Africa? Or bricks made in the Dominican Republic? because the clay is different. The baking process is different. The way they make it and the materials they use is different. Is it a 10 dB wall, or a 5 dB wall, or a 15 dB wall? I don't know. You're going to have to go measure. Same thing with racks. I get that question all the time. Fernando, you have a table that shows me how many dBs I lose across a rack in a warehouse? A rack full of what? Food? Dry food? Cans? Because let me give you an example. I was helping these guys remotely. They were working at these Coca-Cola plants, drinks. And then they showed me a warehouse. They had no racks. Okay. And then they brought pallets and it was filled all the way to the ceiling with Coca-Cola cans, metal aluminum cans filled with fluids all the way to the ceiling. What are waves going to go through that? Yeah. And then the next day they show me like, look, everything is gone. There's nothing. So those waves are just going to travel freely throughout the warehouse. Then the next day it was filled up to the ceiling of 2-liter plastic bottles. What are waves going to do through that? And what's the attenuation index? I don't know. You're going to have to go measure. It's just waves, it's just energy, and it goes through the laws of physics. If it's open space, it will attenuate at that rate. Double the distance, quarter the power. Double the distance, quarter the power, or minus 6 dBs all the time. So let me explain another thing, because I had people ask like, why do we use dBMs? If this is power levels, why don't we just use milliwatts? That should be simpler. And here's the reason why we use dBMs. And now here's the other thing. Once we were installing those zeros, of course, I don't have my 4 radio. Where's my 4 radio? I'm gonna have to go get it from the other room. When we were installing these access points, arrays from zeros in the schools, like a flying saucer looking thing, parents started coming, and we did have to talk to many of them because they said like, hey, I need to talk to the principal, the headmaster of the school. Like, why? Like, well, my son said you guys have been mounting those modems, those, routers, the Wi-Fi things up in the ceiling. And I read on Facebook that causes cancer. So since I read on Facebook, it must be true. Then I'm really concerned about the health of my child. Okay. I don't know if you had those conversations with people before, but I've had quite a bit of those. And here's why. I'll explain to you why this is such a small amount of energy we're dealing with here when we're talking about Wi-Fi. So in your designs, Dan, what's the target signal that you want for your clients to work?
Depending on what frequency, we're looking at a minus 67 dB for 5 gigahertz, maybe minus 70 for 2.4.
Okay.
But there's no right or wrong. There's no one size fits all. Don't think.
But that's a good start. Next 67. Why next 67?
Maybe historically, I feel like a lot of iPhone devices started roaming around the next 70 mark, and we just sort of wanted to almost push them off that cell to move on. So I think it sort of stuck with us.
So basically, next 67 has been proven to be a really good, strong signal with lots of energy for these devices to connect and have a good conversation. That kind of agree on that?
Yeah, I guess so, yeah.
Okay. All right. Lots of energy. Strong signal. How much energy then are we talking about? Because that's kind of like what we were, back then we were delivering next 72. And yeah, next 67, next 65, in that range. Okay. Well, my screen on your screen?
It's blank page, but yes.
Yes. So if we have 1 watt Well, actually, if we have a 65-watt light bulb, you know, it lights up your room. In a fridge, they're like 25 watt light bulb. If you have a 1 watt LED, we can relate to that. 1 watt. If we divide this by 1,000, we end up with 0.1 1,000th of a watt. How do we also call this unit? 1,000th of a watt. What's the short name for that?
Milliwatt.
1 milliwatt. 1 milliwatt is 1,000th of a watt. That's the unit of power we're using. Right here is where we start with 0 dBms. Remember, dBs are used to compare things. dBi compared to an isotropic radiator. We saw that when we saw antennas. Then plus 3 dB gain, plus 6 dB gain. You're increasing the gain on one side, of course, decreasing it on another. But then we started with 0 dBis. 0 dBi was an isotropic radiator. And then as you started increasing the gain in the horizontal plane, you started increasing dBis. A 3 dBi gain antenna, a 6 dBi gain antenna, a 13 dBi gain antenna. Power. We use 0 dBms to mean 1,000th of a watt. Right here. Right there is where we start. Okay. So let's say 0 dBms, that's 1 milliwatt of power. If we go to minus 10 dBm, what does minus 10 mean on the other side? See, we're going back to a trick we learned this morning.
Times 10.
What's that again?
Oh, hang on. No, sorry. Divided by 10.
Divided by 10. So if I divide this by 10, I end up with 0 point, and I'm just moving the decimal point, a tenth, 100, 1,000, 1/10,000th of a watt. If we go 10 more dB down to minus 20 dBm, what does minus 10 mean on the other side?
Divided by 10.
Divided by 10 again. So now we have a tenth, 100, 1,000, 1/10,000, 100,000th of a watt. Go down 10 more dB to minus 30 dBm. What does minus 10 mean on the other side? Divide by 10 again. Now we have a tenth, 100, 1,000, 1/10,000, 100,000, 1/1,000,000th of a watt. Remember, this energy leaves the source really strong, 1 milliwatt. And as those waves propagate and dissipate and attenuate at that rate that we've been talking all morning about, double the distance, quarter the power, they start getting weaker. If the energy is minus 30 dBm, we have 1/1,000,000th of that watt. If it goes down 10 more dB to minus 40 dBm, divide by 10. Now we have a 10, 100, 1,000, 1/10,000, 100,000, 1,000,000, 1/10,000,000th of a watt. We go down 10 more dB to minus 50 dBm. Divide by 10. I have a tenth, 100,000, 1/10,000, 100,000, 1,000,000, 1/10,000,000. Where am I at? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 8. I think I went one too many, didn't I? A tenth, 100,000, 110,000, 100,000, 1 million, 110 million. Oh yeah, 100 millionth of a watt. We go down 10 more dB to minus 60 dBm. What does minus 10 mean on the other side? Divide by 10 again. Now I have tenth, 100,000, 110,000, 100,000, 1 million. 110 million, 100 million, 1 billionth of a watt. Go 10 more dB down, minus 70 dBm. And I'll stop right here because Alejandro's getting impatient. Like, okay, Fernay, we get it, we get it. Gotta go bake my steak, my Argentinian steak. Divide by 10 again. A tenth, 100,000, 110,000, 100,000, 1 million, 110 million, 100 million, 1 billion, 110 billionth of a watt. And you said, Dan, you designed for NEC 67, right?
Yeah, usually.
So somewhere in between 1 billion and 110 billionth of a watt. This is why, my dear friends, we do not use milliwatts when we are designing Wi-Fi. Because can you imagine them presenting to one of your customers like, yo, we're going to design your network to work at 0.000000005 watts. And I say like, is it going to work? Yes. This is why we use dBm. When you said next 67 without any hesitation when I asked. You didn't say, look, well, I designed my networks for 0.0000005 watts for Nate. That's what we do. That doesn't sound good. It's complicated. You lose track of all these zeros, and it's simpler to use dBms. And this is the amount of power these Wi-Fi devices are dealing with. They're sending billions of bits per second at energy levels that we cannot see, we cannot hear, we cannot measure, we cannot sense, we cannot smell. It's not like we go into a room and go like, oh man, 100 milliwatts, we gotta change that power. Like, no, you don't sense it at all. We don't see it. That's why we need tools that would help us sense this energy. The power amplifiers of these devices have to be so good, and the digital processors have to be so good to process these waves at these minuscule amounts of power levels and still make sense of what's happening. Right now, I'm talking to you and I'm seeing you. Well, the ones that have cameras on, I don't see the ones with cameras off, but all of this stuff is happening through those waves because I don't have an Ethernet connection. I don't have a wire. It's all Wi-Fi. Isn't that wonderful? This technology is so beautiful that it's amazing that it works. And you, sir, you're worried about your son getting cancer from these devices at NEC 72 when you're giving him a phone and he's talking to grandma and putting this that transmits at from 1,000 to 4,000 milliwatts right next to his head, and you're blowing smoke on his face as we're talking, and you're not worried about either one of those two, but you are worried about this Wi-Fi stuff. This, I don't know, there was something in Ireland that this family took their kids off school and they were homeschooling because since they put Wi-Fi in that school, their kids were experiencing social anxiety. And then they thought because of the Wi-Fi energy that was affecting them. So they lived in their house and they were happy. Like, these waves are so minuscule. They are, so far, I personally haven't seen any studies that show and have a correlation of Wi-Fi devices affecting, the well-being of humans around it. I mean, I've grown a couple of moles in here, but I don't think it's because of any of this stuff. But so, dBms is what we use to measure this energy that we're dealing with. And yes, we use this type. Let me just add another page in here, because here, let's just wrap it up with this. If this is an exam, this is an example, an exam question that you might get on the CWNA. Let's say you have a transmitter injecting 100 milliwatts of power into a system. You have a cable connected to an antenna. In this cable, you lose 3 dBs, okay? The antenna is a 7 dBi gain antenna. The energy that leaves the antenna, this is what's called EIRP, effective isotropically radiated power. What is the EIRP of this system? So basically, how much energy is leaving the antenna? Let's play. So let's convert all of these units into dBs. All right. We already did 100 milliwatts. How do we get to 100 if all you have is division, multiplication, tens, and twos? Dan, you did this one?
10 times 10.
10 times 10 gives you 100. What does that become then if we want to convert that to dBs? I should have done this 10. The other. Here, let me just do it in the same way we did it earlier so we don't get confused. So 10 times 10 gives you 100 milliwatts, of course, we're talking about. And then that becomes 10
plus 10.
Plus 10, which meaning this is same as 20 dBms, right? 100 milliwatts is equals to 20 dBms. Now we know where it comes from. So now we have all in dBs, and don't get thrown away by having an M in here and an I in there and no unit in here. It's just all dBs. It's just straight math. So we just do basic math. 20 dBms is what's injected. You lose 3 dB in here. So what do you have now? You have 17 dBs. But then you, because this is a loss, you're losing that energy. You're basically losing half the energy, because minus 3 is what? Divided by 2. You lose half the power on the cable, and then you gain 7 dB in the antenna. So now what do we have?
24.
You have 24 dBms. Man, I'm just sloppy here. Let me just delete all this stuff. We have 24. That is the EIRP of the system. Okay. Now, how many milliwatts then is this? We already did this one, but let's do it again. How do you get to 24 dBms? If all you have is plus, minus, tens, and threes.
10 plus 10.
That's
plus
20.
10.
30.
Minus 3, minus 3.
27, 24. Okay. And that becomes?
10 times 10 times
100,
10.
1,000.
Oh, divided by 2, divided by 2.
500, 250.
250.
So 24 dBms is equals to 250 milliwatts. See, you inject 100 milliwatts. Let me just use a different color. You inject 100 milliwatts of power and then you lose some in the cable, and then you gain with the antennas, and then this is actually what leaves your antenna. This is the effective isotropically radiated power, which this is what the FCCs of the world, Ofcom in the UK, and the, I don't know, what is in the Dominican Republic, Luis? El Ministerio de Telecomunicaciones, or I don't know, whatever it is.
Yeah.
This is what they regulate, where they say you cannot do, let's say, more than 1,000 milliwatts, or you cannot do more than 30 dBMs. Now, what's more, 1,000 milliwatts or 30 dBMs? Ooh, which one's stronger? How do we get to 1,000, or how do we get to 30? Well, we have it right here.
dBm.
So
10 plus 10 plus 10.
10 plus 10 plus 10, that's 30 dBm, right? How many milliwatts is that?
1,000.
10 plus 10 plus 10 becomes 10 times 10 times 10. That's 10 times 100, that's 1,000. So 1,000 milliwatts. So which one's stronger? It's the same. And some documents will show you, oh, we recommend that these guys are configured at 14 dBMs. Okay. And how many milliwatts is that? Just do the math, and then, it's just the equivalent of one or the other. So this is an example of things that you're going to come across in the CWNA exam, for those of you who are going to take the exam, that you have to calculate and put these things in the same unit. Same thing with phones. You buy a phone and it's put in a warehouse, and in the spec sheet, it may tell you, we recommend that these phones, have the access points configured at 17 dBMs, or they have configured at whatever value in dBMs. And then other companies, they use milliwatts. It's okay. They use one or the other. But then here is where we have to understand that when we're talking dBM, we're just talking about a unit that is equivalent to something in milliwatts. And then the amount of power we're dealing with in Wi-Fi, when you talk next 67, next 65, next 72, it's minuscule. It's not that harmful, because people think that this Wi-Fi device, let me just give you another example. At a school, I got a ticket to go and move an access point out of a room. So I go there and say, yeah, I'm here, have this ticket to move I thought the access point was like blocking something, or the lady said like, oh yeah, since they put that Wi-Fi thing here, I've had headaches every single day. I'm like, oh, I'm really sorry. So what I did, I disabled the LED lights, little blinky lights. I turned them off. I came back a week later and I asked the lady, so ma'am, I'm just here to check, because I couldn't move the AP, but I turned it off. And she's like, oh yeah, thank you very much. Since you turned that access point off, my headaches went away. Oh, thank you, I'm so happy. I never turned the AP off. I just turned the LED lights off. If the AP is off, how do you think your 40 Chromebooks are working? Huh? See, it's just like, people think this is going to affect them tremendously. It won't. Just very, very small amounts of power. So dB math, that's something that we as Wi-Fi professionals have to know how to deal with. And this is the reason why we use dBMs and not milliwatts when we are doing our designs and when we're doing this. Now, software will do all of this math for you. When you are doing a design, then the software, when you place an access point and you give it a transmit power, you got to be careful, because is it the transmit power or is it the EIRP, what we are putting in there? If we're using Ekahau and you put in an access point and then you look at the power you're given, it shows you, I have this much power and I have this antenna gain, then this is the effective isotropically radiated power leaving the antenna. Okay? This is why when you have certain, I know Cisco will do it, that if you have an access point with external antennas, And you say, like, I want the power to be this. Like, whoa, wait a minute. What type of antenna are you plugging into this access point? And what is the gain? Because if you have, let me just share here really quick. And with this, we'll wrap it up. If you have this same scenario, let me just use a different color. But then you add a 17 dBi gain antenna, not a 7 dBi, a 17. So we have 20 dB of power being induced right there. You lose 3 dBs on the cable. You have 17. And then you add 17 dBi gain antenna. What is the EIRP now?
34.
34 dBms.
But that's beyond.
How many
regulation.
milliwatts is that? How many milliwatts is 34 dBms? So we stop here at 1,000, right? Let's just do it again. How do you get to 34 if all you have is plus minus 10s and 3s?
10 times 10 times
4,
10
4,
times
10
10.
plus.
Plus
Oh,
10,
sorry, 10 plus 10 plus
plus
10, yeah.
10,
10.
plus 10, okay.
Minus 3, minus 3.
And that on the other side becomes
10 times 10
10
times 10 times 10. Divided by 2, divided by 2.
Okay. 10 times 10
100.
times 10
1,000.
times 10
10,000.
divided by 2.
5,000.
5,000.
5,000 divided by 2.
2,500.
2,500 milliwatts. If you are in a place where the maximum EIRP you can transmit is 30 dBms, you're over. You're in violation and you can get in trouble, and then you'll be out of compliance. So that's why they ask you what it is the gain of the antenna you're plugging into this access point, because then it will do all the math and know how much you lose here, how much power you can inject. So it's like, oh, if 30 is the maximum, you have a 17 dBi gain antenna, then my transmit power is going to have to be lower. How much lower? Well, low enough that it's going to stay within the 30 dBm requirement. Okay? So it's going to be what? If I added 10 in here, you just remove 10 in here, so you can only go 10 dBm on this side. So just 10 milliwatts. All right. Questions, comments, insults? No? All good so far? With this, my dear friends from all over the world, thank you for coming. We come to the end of this session 345 of Tesos and Wi-Fi. Now, bringing this free wireless LAN professional Wi-Fi design class for free, 100% free, 98% in English. And today we talk about DB math. Hiten, you have a question or are you just saying bye?
I have a question, and if you have time and convenience, can you kindly revisit the maximum question you had puzzled the Cisco engineers yesterday? I was watching in the recording. I didn't get it real right. If it is okay and you have time, I understand, you know.
What was the question? You haven't asked the question.
About the zero max. What's the max value? If I recall it right, what's the max you have? And you got varied answers saying that it depends upon the environment and outside of Cisco.
You're talking about when we talk about power level 1, that's the maximum power. Well, yeah, yes. It depends on the regulatory domain, because even like here in the US for Uni 1, I believe it's 30 dBms and there's 36 dBms on Uni 2 and Uni 2 extended. But other countries, their maximum is probably 23 dBms for Uni 1, and what is 30 for Uni 2 or Band C, Band B, I mean. because you have band A, band B, and band C, correct? So you have different limits, and it changes per country, per regulatory domain. So yeah, it just changes. So power level 1 is the maximum on that regulatory domain on those specific channels where you are. But regardless, once you know what the value is in milliwatts, you can now convert it to dBm or vice versa. Because again, there is not a rule that says you have to use milliwatts or you have to use dBm. And vendors use them interchangeably. Data sheets of devices, they will tell you what the requirements are or how much transmit power they have. And if you go to the FCC data sheets for devices, they say, oh, this is rated at whatever dBms does the transmission. Or if you look at testing results, they say we tested the devices and the transmit power was this many dBms or this many milliwatts. That's what we are covering here today. So today we learn about dB math, how to convert from dBms or dBIs to milliwatts, and just went through the basics of what they call the tens and threes rules. That's just a trick. It's a trick like I don't know, a trick that they taught you when you were a kid, that if you look at your knuckles and you look like January, February, March, April, May, the months that landed on the knuckle were the ones with 31 days. Play that game when you were a kid? No? Like maybe just us? That's a trick. Here's another trick for you. Okay, ready? 9 times 5. 1, 2, 3, 4, 5. If I hit that 5, what do you have on each side of the finger I hit? You have a 4 and you have a 5. 9 times 5, 45. See, it's just a trick. 9 times 7. 1, 2, 3, 4, 6, 7. If you hit the 7, what do you have on each side of that finger? I have 6 fingers on this side, 3 fingers on this side. 9 times 7, 63. Just a trick. That would have been helpful back when we were in elementary school, huh? Just a trick. There's nothing to it. What we learned today, the tens and threes rule, the plus becomes a times, the minus becomes divide, the 10 is a 10, and the 3 is a 2. That's just a trick to convert from dBms to milliwatts and vice versa. Thank you very much all for coming. This is the end of session 345 of Tesos and Wi-Fi. This is part of the free Wireless LAN Professional Wi-Fi design class that we bring to you all over the world in English this time. I know we've been doing this in Espanol for our Spanish-speaking friends. Now this is also recorded to the Wi-Fi-of-things.com. You go to that website, every single session we've recorded is up there, okay? Now you know, free love for everybody and free Wi-Fi training for everyone. Thank you very much. Have a great day.
Thank you.
And have a great weekend. I forgot it was Friday. Hey, not a problem. Thank you.
And it's a long weekend here in the States.
All right. We have a holiday weekend coming up. And I'm preparing for classes in Memphis next week. I have the troubleshooting class, and then the week after is going to be in Montreal in Canada. So I'll see you around. Take care.
Thank you. Bye-bye. Take care. Bye-bye.